Alright, boys and girls, video 32. Hopefully you're hearing me. Yeah, it looks like I've kicked in. Okay, good. Guys, threw you a little bit of a curveball, and I want to explain what's going on. I thought that after video 31 was a natural place to end before assignment number 4 is due and before our July 19th meeting. And, I slept on it, thought about it, really kind of tried to get a better overall picture of what we're trying to accomplish here. And fortunately, unfortunately, depending on how you look at it, we need one more video in before you actually submit assignment number 4. Now, if you're listening to this video, then it's clear I'm going to make the announcement in class. By the time you see this video, it will already be made in class in our June 28th meeting. I also changed it on the syllabus when it was updated, I think June 25th. So sorry, but I still think it's the right thing to do. It's going to be a lot, a lot of video, a lot of information between our June 28th meeting and our July 19th. But the good thing about that is it's going to make it easier as we transition on out at the end of the semester when we look at the final things of the final topics of the semester and get ready for the final exam. So guys, video 32, it's going to be, this is going to be more on matrices. So I'm just going to call it more on matrix methods. And the purpose here, or the overarching goal, if you will, is to examine matrix methods as it comes to the ANOVA for regression. Now, oh, by the way, I got new headphones. My wife got me some Bose headphones with the speakers, so I'm just curious if there's going to be any difference in the quality. You guys can keep me posted on that. But let me explain the difference. There's always a lot of debate, confusion. I was confused. Most statistics students are confused about the ANOVA for the difference in means and the ANOVA for regression. Now, guys, obviously what we're going to be doing here is the ANOVA for regression. This is going to be the focus of this video, and really from here on out. The difference is this: if we want to examine, well, let's just go back to what ANOVA stands for. It's an acronym for analysis of variance. So analysis of variance gives us a method for analyzing the variation in our model. So guys, if we're interested in taking population means and drawing a sample from each one, then we would be interested, first of all, if we can imagine, a grand mean here. We would be interested in, first of all, looking at the variation between the distributions with a variation within the distributions. Now, there's a ratio of the variations between, the variations within, called the F statistic. ANOVA was developed by a guy named Fisher, and hence we give it, the F statistic. I wish it had been named by Darbro. We'd have it the D statistic, but that just didn't happen. Okay, so in this situation, we got ANOVA, which is examining the partition of variation in this setting, but our ANOVA for regression is examining this. First of all, we've got, our points. Pretend you can see those. Okay. All right. We've got our y bar. And we seek here, let's get some more points up here. For example, if we just want to examine this point right here, we want to look at the variation first of all from our observed y to the mean. And then we want to break that partition into two parts. First of all, we call this the ANOVA for regression, and we call this our, well, we don't call it ANOVA for regression, we call it our sum of squares for regression. And we call this kind of partitioning out the variation of our error. So again, confusing. If you're confused, welcome to the crowd. We all are at first. But you got to understand, ANOVA for regression, ANOVA for independent samples means with more than two groups, is essentially looking at the partition variation in our models. So guys, we're going to look at the all right, so let's clear out the screen right here. All right, guys, what we looked at last time is that we can look at the coefficient vector, the estimates of the coefficient by looking at this vector, which can be, pretty easily found. By looking at the product of these vectors. So we have to take the inverse, have to look at the transpose, and so on and so forth. We also saw that we can do the residual vector by taking x times b. So whatever we find right here, remember our x is our design matrix, and so far this just looks like this. And yes, Denise, the ones are important. And then we look at the residual vector, which we will call, I guess, E. Not like I made that up. Which is the observed y's minus the predicted y's. Or the fitted y's, depending on how we look at it. So, but guys, it's easy to see that this is just going to be the response vector minus the fitted value, or the observed, the product of our design matrix and a beta matrix, or beta vector. All right, gang. Now, guys, remember, what do we seek to do in ANOVA? In ANOVA for regression, we seek first of all to look at the sum of squares for the total and see that that can be broken down into the sum of squares for the error down to the sum of squares for regression. Sum of squares for error plus sum of squares for regression is equal to the sum of squares total. We can then come in and divide each one of these by its degrees of freedom. And we'll get the mean square total, mean square error, and mean square regression. Remember, guys, mean squares are not additive, so the mean square error term, well, the mean square error plus the mean square regression will not sum up to be the mean square total. What we can then do is we can take the mean square regression and the mean square error. We can create our F statistic by taking the mean square regression divided by the mean square error. This F statistic will follow the F distribution with degrees of freedom, well, in what we have so far, a 1 n minus 2. Now, 1 actually stands for the number of predictors. After this video, we'll start multiple regression where we'll get into multiple predictors, and this one will obviously change. All right, gang. Let's remember sum of squares for total is where we started one of these lectures many moons ago, and remember that this is just the difference in our observed and our mean quantity squared. Now, it can be shown, and it's very helpful in this situation, that we can rewrite this. And I haven't decided yet whether I'm going to require this to be a homework problem or not. I don't think it is, because I think you've got enough on your plate for assignment number 4 without me throwing some more stuff at you. So, but this is a well-known fact that that these two are equivalent, and I really encourage you, and in all your spare time, right, to see if you can to make that connection. And it's actually very, very simple, actually. And guys, we also know that to I don't know. Let's see how I want to put this. Well, I'll tell you what. Let's focus on this right here. To examine the sum of the observations, the y observations squared. What we're going to look at is we're going to look at y transpose times y. And if you think about this for more than half a second, makes it very clear. When you understand just a little bit about how matrices are multiplied. So, Chris, I think you said this is the way you teach your kids. No, I do too. So here we have a 1 by n. Here we have an n by 1. So these n's are the same. So we can multiply them and get a product, and the product is going to be a 1 by 1 matrix. And guys, by taking linear combination, we have y1 times y1. Linear combination, y2 times y2. Do that for all of the terms. And it's really, really, really easy to see why this indeed is what we need back here. Now, on the next screen, what I'm going to do is we're going to come in, we're going to examine this term. Man, you got a lot going on the screen, don't we? Me circling and pointing and doing all sorts of stuff. Next thing I want to do is examine this part right here. So, that was just the ugliest summation in the history of summations. So again, we're going to examine this. Now, guys, something shows up a lot in statistics that's called a J matrix. And a J matrix is a square matrix. So we'll say it's just an n by n matrix. And turns out it's really easy. It's a matrix just all ones. And if it turns out that well, I'm trying to think how it actually does work out, but once I get the pencil to the paper, it'll hopefully come back to me. J matrix, so if we have, for example here, if we have, you know, a 2 by 2 matrix, then the J matrix is going to be one of the easier ones you'll ever come up with. It's just 1, 1, 1, 1. Now, so what I need to do here is I need to bring this into matrix methods. I'm writing real slow because I'm thinking. Oh yeah, okay, just yeah. And it turns out that we can look at this as 1 over n times. Do you guys hear that? I guess that's a stupid question because you can't answer me. I guess you can answer me next time we see each other. By taking y transpose j times y. Now, you know, I think first and foremost, you know, y, and are you sure? And then yeah, I'm sure, or I'm pretty sure. But if you think about this, let's just set up you know, just a simple matrix. Let's let y1 be 1 and y2 be 3. So first of all, no, I don't want to do that. First of all, if we take the sum of the y's quantity squared over n, we're going to get 1 plus 3 quantity squared over 2, which of course is going to be 8. Now, examining the matrix method, which is going to take, you know, 1 over n, so we're going to have 1 over 2, times y transpose. So remember, guys, the response vector is a column vector, so the transpose is going to be a row, times the J matrix. So we have two y's, so we're going to have a 2 by 2. And times our original y, our response vector, which is 1, 3. Now, I'm going to have to go to another page to do this, but let's just examine, let's just not even worry really about the 1/2 right now. Let's just examine what happens when we multiply the vector 1, 3 times the J matrix. Well, clearly what happens is we have a 1 by 2, we have a 2 by 2, so we're going to end up with a 1 by 2 matrix. Okay? So hopefully that by now we're pretty decent in multiplying these two things together. So we're going to go 1 plus 1. I'm sorry, 1 times 1 plus 3 times 1, so we're going to get 4. And the other, we're clearly going to get 4 as well. So keep the ball rolling here. When we have 1 over 2, 1, 3, 1, 1, 1, 1, 1, 3. This part right here is going to give us 4, 4. I think that's right, wasn't it? All right, gang. Again, let's not worry about this, the 1/2 just yet. So we have a 1 by 2. We have a 2 by 1. So we're going to end up with a 1 by 1 matrix. So if we take 4 times 1, So we're going to have 1/2 times 4 plus 12 is 16 divided by 2, which is also equal to 8. Now, guys, clearly not a proof. So what I would hope that you'll do is I hope that you'll verify given in, let's just call it y sub i's, that 1/2 does indeed equal this. All right, let's go on. And so, guys, it follow well. It should follow that if the sum of squares for the total is equal to, let's go back here and just make sure that you know what the connection I'm trying to make here. If the sum of squares for the total can truly be rewritten, again, this right here, and the equivalent matrices are what I've shown you. Then sum squares for the total can be written this way. Now, I think I want to examine the sum squares for the error. And, you know, just like we had before where the sum of the yi squareds can be rewritten as y transpose y, it should follow that the sum of the errors squared it should follow that we take the error vector transpose times the error vector. So we know from before. Let me start new. We know that the sum of squares for the error which is the sum of the e sub I squared, which is the sum of y sub I minus y hat sub I quantity squared. Huh. My pen's not writing as well. Should lead us to, without a whole lot of craziness, this. Because, guys, remember this, this part would be, you could think of it as the, how we calculate the errors, transpose, and this would be the errors. And I think there's a simpler way. Let's see, we'll have y transpose times y. And then we get into that thing we got in before, so we got beta transpose x transpose y. Yes. So that's exactly what I want for, let me think about this. I don't think, it's not, okay, y transpose y minus x beta transpose, which is going to see x beta transpose will be x transpose beta, then the transpose of that's going to be beta transpose x transpose y. Yeah, perfect. All right, gang. So guys, clearly we know that the sum of squares for the total is equal to the sum of squares for the regression plus the sum of squares for the error. So finally, it should be no surprise that we can show that the sum of squares for regression is going to be the sum of squares for the total minus the sum of squares for the error. And it turns out that this can actually be shown to be beta transpose x transpose y minus 1 over n y transpose j y. Okay, guys, I'm struggling here. Something doesn't seem to be setting just right for me. So y transpose, so sum squares for the error. So we've got the total. Okay. Yeah, this term. Okay, yeah. All right, gang. Looks good. So, guys, what I've shown you now is using matrix methods, you know, how to come up with the sum of squares for the total, sum of squares for the error. Really, in your calculations, you just have to do 2 of these, because if you can determine 2 of the 3, then you can clearly determine the other. It seems to me that the sum of squares regression is given last, because the calculation, you know, of these matrices, the product of these matrices and the difference actually turns out to be a little bit tougher. Now, guys, going to move forward. We're going to be talking about or at least move this into the inference part. And what I'm trying my best to do is I'm trying my best to be consistent. I know sometimes when you're learning, you're kind of thrown to the wolves, if you will, and it's hard to see the bigger picture. What's the saying? You can't see the forest for the trees or the trees for the forest or something like that. I've never really understood which one of those is supposed to come first. It's kind of like my buddy's convinced that if you, what is it? Liquor before beer, have no fear. Beer after liquor, never sicker or something. I think that's pretty silly. But so that was a tangent. I have no idea where that came from, but that was a true tangent. So, guys, let's recall. Well, I'll be darned. I just figured out how to adjust this thing. Well, I am so proud. That's not bad after 32 videos, actually 33 videos. Okay, guys, anyway, recall we've talked about something called a variance-covariance structure. And remember again, our beta matrix here is beta 0, beta 1. The variance of B It's hard to write this small. Really having to concentrate. It's kind of weird being quiet. Is this. Now, we call it variance-covariance because we get the variance and the covariance. The variance for our intercept is what's given here. You guys always remember, I missed a problem like this back in grad school. I forgot to take the square root. Remember, gang, you got to take the square root of the diagonals to create the variance. These values here give the covariance between the slope and the intercept, b0, b1, and those will always be the same value. You can think of it kind of as kind of the correlation, but it's actually referred to as the covariance. But what we typically are interested in here, we're typically interested in these values right here. The reason being is these values right here are very important in the inferential part because it gives us the standard errors for our B0 and our B1. So, and again, remember, you got to take the square root of the values on the diagonal or you're going to miss the problem. So guys, our estimate, we use S squared beta as an estimate of this, and this right here, as we've seen before, can be found by taking the mean square error, x transpose x, times the inverse. So if you think about it, and the key ingredients of conducting inferential analysis is your test statistic, which is t, which will typically be our b1 minus our beta 1 divided by our standard error. And so being able to find the standard error is clearly important because you can't find your test statistic without it. And guys, remember, this leads to our p-value, which is calculated under the t-distribution with a specified degrees of freedom. Now, let's get into something really cool. This is something I kind of think is fun, if you will. So let's get into our mean response. Now, guys, it's been a few videos since we've investigated this, but let's say we come up with a model to predict. I think the one we used before is we could predict first year college GPA from someone's ACT or even high school GPA, and if we examine someone with let's just say we're looking at ACT as a predictor of I don't know, let's just say Calc 1 grade. Let's say we live in a fun world where everybody takes Calc 1. And you come up with some model where you can, have your Calc grade as, some value plus some value times your ACT. And clearly we're going to call this beta 0. Clearly we're going to call this beta 1. Now, if we want to find, for example, we want to find the predicted Calc grade, and guys, we'd have to run this from 0 to 4 because we'd have to have quantitative data. So we're looking in terms of quality points. So if we want to put in an ACT, for example, of 26, now we're going to predict a Calc 1 grade, but we have to understand there's going to be variation in this. So what we have to do is we not only have to get our point estimate, what's the estimated calculus grade from an ACT of 26, but we have to understand there's going to be natural variation within the prediction. Not everybody has a 26 is going to go out here and make the same calculus grade. That's just where kind of statistics is put on the back burner, a little bit of common sense kicks in. So because the scores are expected to vary, we also want to be able to explain the variation in the mean response. Well, I think this is just cool as hell. And I had to go back and actually look this up because I forgot this. We actually end up getting a new vector, which is we call x sub h, just like we did before. And this vector is a really simple one. It's just a 2 by 1 vector, which is 1 x of h. So guys, clearly we're going to probably need this. X transpose is just going to be this vector. All right, now we know that our predicted value in general is going to be x times beta. Well, in this situation, because we need, we're going to need the, all right, so if we're going to get this, we're going to have to look at the transpose times the beta vector. All right, guys, I'm gonna have to justify this. Okay, let's examine this a little bit closer. So we got x h transpose beta. So this is going to be 1 x h 0 beta 1. Which is going to be beta 0 plus beta 1. X, that should, guys, that's an XH, just make sure. XH, which is going to be the Okay, so that's going to be the just the predicted value. Which is exactly what we need. Okay, so I did get it right. Yeah, I couldn't remember whether it was X transpose H or... yeah, well, it has to be X transpose, because if we just had... Think about it, guys. If we just had XB, in this case, we would have a 1XH. So we would have a 2 by 1 times a 2 by 1, which doesn't have a product. So, guys, we had to use the... All right, cool. So again, we can predict the mean response by using this matrix method. Now let's examine the variance. Let's examine the variation. And guys, the variation here is going to be X transpose H times the variance of our beta times our XH. Yes. All right. So let's see now. So this is actually going to be what we're going to use to estimate this. Is going to be our mean square error times our X transpose H times this bar right here is going to be our X transpose X inverse times XH is going to be this. Yes, yeah, okay, perfect. So, let me see how much time we've got. I don't know if I've got time in this thing to actually work through an example. It would be really nice if I do, but I don't really have any data. I got 44 minutes. I think it'd be a good idea to run through an example here. It's going to take a little while, but I think it's going to be good to do this. Let's say, for example, that we're going to be working, let's just choose some data like this, and so if we go back, and actually it's going to take forever to do this. guys, I'm going to trust that you can handle this, because really, as I break down the parts, as I think about breaking down the parts, there's nothing that we've really done. I mean, the final answer looks pretty crazy, but there's really nothing that we've done that, when you break it down piece by piece, doesn't follow naturally from the other illustrations. For example, in finding the mean response, we're going to have to take look at the product of these two matrices. Well, actually that's pretty easy, right? And when we start looking at the variation, at the variance, well, mean square, we know how to do that. And this actually isn't that hard either, because we've examined this part, and these two matrices right here, actually first one's a row vector, second one's a column vector, are not that difficult either. So, guys, I will end this, and I promise you that this will be the last video before our July 19th meeting and before your assignment number 4. So I'm not going to throw anything at you. The next video we put up will be multiple regression, but I think it's pretty clear. Plus, when you see your assignment, you're going to know it's really clear that we needed to get this video in before we actually went on to almost a completely separate thing. Because, guys, you got to remember, if we can get and you got to trust me on this, if we can get a solid understanding of simple linear regression of matrix methods, matrix operations, it is going to be a piece of cake when we get into multiple regressions. Now, there's some other stuff that's going to give us some, probably some fit, and that's going to be, examining our best models and things of that nature. But it's going to set the foundation for making things easier in multiple regression and even logistic regression. So guys, that's going to be the end of the video. So have a good one.